This is the point at which our course takes quite a major turn. So far, I've stressed the large-scale, old universe with its stars and galaxies. But now we're heading for the very young universe. Here's our familiar timeline. We've completed themes 3, 4, and 5, and now we're about to start theme 6. So for the next 3 lectures, we're going to be looking at roughly the first second after the Big Bang. Now, it's not too hard to see why this is an interesting time. It's when all the ingredients of the universe were first minted. It's when the protons and neutrons were made that ultimately get combined into atomic nuclei inside stars. It's also when the forces of nature, in fact, all the laws of physics, were busy taking on their current form. So it's really an incredibly interesting time. Now, it turns out that all these particles and forces emerge from an exceedingly hot environment. So the first of our 3 lectures, this lecture, looks at how gases behave at ultra-high temperature. This will give us the necessary background so that next lecture we can look at the emergence of the various particles, and the lecture after that will look at the emergence of nature's 4 great forces and the laws of physics. Now, at that point, we'll be ready for theme 7, which looks at inflation, the actual launching of the universe's expansion, the bang itself. So let's begin by reviewing why we know the early universe was very hot. There are 2 key pieces of evidence. One, the microwave background tells us that it was 3,000 degrees everywhere about 400,000 years after the Big Bang. And 2, the helium abundance tells us it was 100 million degrees everywhere about 3 minutes after the Big Bang. But how do we know what the conditions were like before that time, at, say, 1 second? The answer is basically that we think we know how physics works at these early times. Most importantly, we're confident that Einstein's theory of gravity works just fine in these conditions. And that tells us that at earlier times the universe must have been smaller and smaller. It also helps that the contents of the early universe are simple. A gas of particles and photons spread about uniformly, all interacting with a well-defined temperature. Now, if you put those 2 together and follow the gas back in time so it's more and more compressed, then it must have been hotter and hotter. Remember, photons get more and more blue shifted. Their wavelengths are smaller at earlier times, so the universe was hotter. Here's the simple relation we met in lecture 14 between temperature and the universe's size or scale factor. Temperature is simply proportional to 1 over S. And so as S gets smaller and smaller, temperature keeps getting higher and higher. And so that's why we need this lecture. We need to understand the properties of extremely hot gases, much hotter, in fact, than the center of the sun. So let's get serious and replot that graph using exponential axes. We've got time going along the bottom with a factor of 1,000 for each step, going from 1,000 seconds to 1 second, to a millisecond, to a microsecond, to a nanosecond on the left. Along the top axis, we have the scale factor. So for example, at a picosecond, the scale factor was about 10 to the minus 16. At that time, today's entire visible universe was crammed into a region smaller than the Earth's orbit around the sun. Now on the left vertical axis, we have temperature in billions of degrees, from 1 billion degrees at the bottom to 100 million billion degrees at the top. And on the right-hand vertical axis, we have density in tons per cubic centimetre, from roughly the density of lead at the bottom to 1 million times the density of an atomic nucleus at the top. The dashed line shows the trajectory of the universe's conditions. As time passes from left to right, the universe expands, cools, and thins out. Now, I know this straight line doesn't look much like that other graph, but that's just because we've switched from linear to exponential axes. Otherwise, it's exactly the same. So let's just pick a couple of times to get the hang of things. At 1/10 of a millisecond, it's 1,000 billion degrees and nuclear density. And at 1 second, it's cooled to 10 billion degrees and thinned out to a ton per cubic centimetre. Now, you may be wondering how it's possible to know anything about such outrageously high temperatures and densities. But it turns out physicists have been studying these kinds of conditions for quite some time. So let me explain how they do it. First of all, remember that temperature is simply a measure of the speed of particles, like protons or electrons, how fast they're moving. See, the higher the temperature, the faster they're moving, the higher their energy, and the more violently they collide. So if we want to study very high temperatures, one approach is to accelerate individual particles to very high speeds, arrange for them to collide, and then study the collision. For example, in a 10 billion degree gas, protons move at 8,000 miles per second across the world in 1 second. So if we can accelerate a proton to this speed and make it collide with another proton, then in a sense that collision is a miniature version of what happens within a 10 billion degree gas. I know it sounds a bit crazy, but this approach has proved to be a fantastic way to study the early universe. Now, as it happens, for other reasons, physicists have been accelerating particles and studying their collisions for decades. But ever since the 1970s, it's been realized that this branch of physics, it's called high-energy physics, also provides access to the early universe. In a very real sense, these particle accelerator machines are able to recreate for a fraction of a second a microscopic realm of the Big Bang, right here on Earth. It's really quite amazing. So let's take a quick look at these particle accelerator machines and their detectors. So the first point to make is that these particle accelerators are mankind's largest, most complex, most expensive machines ever made. Here are some of the larger ones. The relativistic heavy ion collider at Brookhaven, Long Island. The Tevatron at Fermilab near Chicago. The Large Hadron Collider at CERN in Geneva. This one in Geneva is about 5 miles in diameter and is buried 300 feet below ground. They all contain huge circular beam pipes, like the ones shown here. The particles that are accelerated are usually protons or electrons, or even atomic nuclei. They zoom around within these beam pipes. And because the particles are charged, they can be accelerated using a traveling electric field. The electric field is like a moving wave, and the particles surf the wave, continually falling down its front, a bit like a surfer continually falling down the front of an ocean wave. Now, typically the ride is pretty brief. It might last 2 seconds, but in that time, the particles may have gone around the ring several 100,000 times and end up moving very, very close to the speed of light. But accelerating the particles is only half the story. You need to make them collide and then study the collisions. Some of the accelerators have 2 beams going in opposite directions, and they cross over at a few critical points around the ring. And at these crossover positions, the particles can collide head-on. So surrounding these collision locations are the most amazing pieces of modern technology you will ever come across. Here's a sketch of the Atlas detector at CERN. And just notice the size of people. These detectors are huge and incredibly complex. Here are some other detectors. They're all basically the size of a building, crammed full of wires and electronics. When the particles in the beams collide head-on, some of their kinetic energy gets converted into mass using E = mc². In other words, new particles are made, and these fly out in all directions. So the physicists use the particle detectors to study the patterns of these collision products, and they can figure out what new particles were created and what their properties are. And that tells them what the conditions were like a split second after the Big Bang. So the all-important question is, what energy do these machines achieve? Or, phrased slightly differently, how close to the Big Bang do they get? Well, back to our time-temperature graph. I've now labelled the right-hand y-axis with the equivalent particle energies. And I'm using the physicists' unit of energy here, the MeV, or million electron volts, along with its bigger cousins, the GeV and the TeV, which are 1,000 and 1,000,000 times bigger. Now, although an MeV isn't much by human standards, in fact you need about 1 billion of them to lift a sugar cube by about an inch, they're actually very beefy units down in the particle world. For example, particles with 1 MeV of energy are found in gases of 10 billion degrees. If that particle happens to be a proton, it's zipping along at 8,000 miles per second, pretty fast. Okay, so starting in the 1950s, as each decade passed, accelerators have grown in strength. And as they've done so, they're able to probe further and further back into that first second. The newest accelerator is the Large Hadron Collider at CERN, that achieves collision energies of 14 TeV, which corresponds to 100 million billion degrees. So it reproduces the conditions about 1/100th of a picosecond. That's 100,000th of a nanosecond after the Big Bang. So, just summarising this last part, although the conditions immediately after the Big Bang seem far, far beyond our comprehension, it turns out not to be the case. Particle accelerators can, in a sense, reach back to that time and recreate it briefly so that we can study the conditions in those first moments. So let's now see what's been learned. How does matter behave in these extreme conditions of ultra-high temperature and ultra-high density? Perhaps the most important property of gases at ultra-high temperature is that a particle's kinetic energy, its energy of motion, can be bigger than the particle's mass energy, the E equals mc squared energy from Einstein's relativity theory. Now, not surprisingly, this kind of gas is called a relativistic gas because its properties are rooted in Einstein's theory of relativity. Now, in these relativistic gases, all the particles behave rather like photons of light. So the gas begins to resemble a brilliant gas of light. And as you might expect, its properties are in some ways much simpler than colder, non-relativistic gases. Now, a second remarkable property of this kind of gas is that when particles collide, just like in the accelerators, entirely new particles can be created. This is the reverse of the more famous conversion of mass into energy. So in these ultra-hot gases, energy can be converted into mass. But as you might expect, in order to create new particles, the gas must be hotter than a certain threshold temperature. Basically, the collision energy must be sufficient to make the new particles. For example, to make electrons, you need a gas above 4 billion degrees, because only then do the collisions go above half an MeV of energy, which is what you need to make an electron out of energy, because half an MeV is the mass energy of an electron. You must have more than that energy to make one. Now, actually, it's slightly more complicated because the laws of nature don't allow a single electron to be made in this way. It must be made along with its antimatter twin, which for an electron is called an anti-electron or a positron. So what actually happens above 4 billion degrees is that particle collisions create electron-anti-electron pairs, and the gas suddenly becomes filled with electrons and anti-electrons. So let's imagine going backwards in time to higher temperature, crossing the electron threshold temperature from below. Here's the situation below that threshold, let's say at 1 billion degrees. We have a gas with a few protons and electrons and many, many photons, and collisions between them simply share the energy back and forth. Now, when we go above the electron threshold, let's say up to 10 billion degrees, the photons and particles now have enough energy to create new electron-anti-electron pairs when they collide. Of course, the opposite can also occur. Electrons can collide with anti-electrons, and we have the famous example of matter and antimatter annihilating to make photons. So above the threshold temperature, all three sides of this triangle are fully engaged, and an equilibrium is established. In particular, the gas is filled with electrons and anti-electrons, about as many as there are photons, and that's a huge number. So, below the threshold, the gas is mainly photons with just a few particles, and above the threshold, the gas is filled with photons, electrons, and anti-electrons. This is really a very significant change. But there's nothing special about electrons. For example, the next lightest particle is called a muon. It's about 200 times heavier than an electron. It's about 100 MeV, rest mass energy. So when the temperature passes 1,000 billion degrees, muon-antimuon pairs are created and added to the gas. And so it goes. Earlier and earlier, at higher and higher temperature, you will find a richer and richer broth containing more and more kinds of particles and their antiparticles. Now here is a graph that shows the number of kinds of particles at higher and higher energy as we go further and further back in time. There's a jump around 1 MeV when the lightest particles are added, such as the electron and anti-electron. And then there's a huge jump around a GeV when a whole new set of particles called quarks get made. Now we'll look at this graph in more detail next lecture, but here I just want you to recognize that at higher and higher temperatures, gases become a richer and richer broth of particles. And at high enough temperatures, all the fundamental particles are present in roughly equal numbers. It's really a very bizarre and amazing substance. Now, while we're talking about all these different kinds of particles, let's just clarify exactly what we're talking about. So here's a famous diagram that shows all the fundamental particles laid out in a nice clean pattern. There are two basic groups. On the right are the particles that make up matter. Collectively, they're called fermions. Lightweight things like electrons or neutrinos are in yellow, while heavier things like the 6 quarks are in mauve. Notice that some well-known particles like protons, neutrons and mesons are not shown because they are composite particles. Protons and neutrons are made from 3 quarks, while mesons are made from 2 quarks. Now, in fact, all the atomic matter in the universe today comes from just the top row, or first family, simply because particles in the other 2 families are unstable and decay into their corresponding first family members. But in the early universe, they were all present in great abundance. Now, over on the left are the bosons, the photon, W and Z, gluon, and graviton. These generate the 4 forces of nature: electromagnetism, weak, strong, and gravity. They also have an odd cousin called the Higgs. It's the only particle not yet discovered experimentally, and creating and detecting it is one of the primary goals of CERN's new accelerator. Now, needless to say, this little diagram is only a tiny bit of an entire theory that describes the properties and behavior of all these particles, and all the laws of nature, really. It goes by the overly modest name of the Standard Model, which obscures just how stunningly successful it is. Essentially, every particle physics experiment ever done agrees with the predictions of this theory, typically to better than 1% accuracy and often much better. The Standard Model is the culmination of over half a century of work, and it gives us the necessary laws of physics to treat the early universe. It can handle the incredibly high temperatures and energies we encounter, and it allows us to follow the properties of the expanding furnace during that first second. Now, having praised the Standard Model, I do want to say that physicists know it's an incomplete theory, and some of the most important ways its incompleteness shows up is in that first second. So in the next couple of lectures, be on the lookout for things that demand that we go beyond the Standard Model. For example, particles of dark matter are not in the Standard Model, but we know they were made in the Big Bang. So clearly, a theory that properly includes dark matter is beyond the Standard Model. Now, at this point, I want to introduce a slightly more sophisticated view of how particles are created from energy. In this view, the particles are, in a sense, already present within the vacuum of space, in a latent form. A modern quantum mechanical view of the vacuum sees it filled with what are called virtual particle and antiparticle pairs, a constant froth of forming and dissolving particles coming in and out of the vacuum. Now, when a real particle comes zooming along with lots of energy, it smacks into these virtual particles and gives them enough energy to change their status from virtual to real. So in the early universe, when everywhere was filled with high energy collisions, one could say the vacuum was fully alive, meaning all the particles of nature that lie hidden within the vacuum as virtual are transformed into real particles. You could say the vacuum is in a state of full creativity. But in today's old cold universe, the vacuum is dormant. The particles and the laws that were once fully manifest now lie hidden within the vacuum. So in a sense, what accelerators do is pump energy into the vacuum to reawaken it. It's the vacuum of the early universe that they're really trying to recreate. And in that reawakened state, it reveals all the particles and the laws of nature. Now, I want to end this lecture by anticipating some possible doubts you might be having about this whole topic. After all, we're sort of used to thinking of astronomical things taking millions or even billions of years. But now we're worrying about nanoseconds and picoseconds. Back to our primary diagram. Almost everything we're going to be discussing in the next 7 lectures happens within literally the blink of an eye. How can so much stuff happen in such a short time? It almost seems absurd. So I want to talk about this possible concern in a couple of different ways. First, let's pose the question a little bit more scientifically. Is there enough time for all these particle reactions to happen before the rapid expansion has cooled the universe down? It's a bit like cooking porridge. Is there porridge on the stove long enough for it to cook? Or do we remove it from the heat before it's had time to thicken? Now, to answer this, we need to compare how long it takes particle reactions to happen, to cook, with how long the expansion lasts, how long the pan is on the stove. It turns out that at earlier and earlier times, the ability to cook was better and better, mainly because the particles were all closer together and colliding more frequently, and also their energies were higher, and this makes them more likely to collide and react. For example, between 1 and 2 nanoseconds, many reactions take just 10 to the minus 18 seconds to reach equilibrium, which is enormously shorter than a nanosecond. So it's like needing a minute to thicken porridge but keeping the pan on the stove for 1,000 years. So the universe can cook, despite its very rapid expansion. And the gas is either in thermal equilibrium or close to it at almost all times. And the changing conditions, for the most part, occur steadily and deliberately. But I'm guessing that still sounds a bit too technical. What about your gut feeling that surely not much can happen in such a short time? But the reason we're suspicious is that it's very difficult to conceive of things occurring much faster than we can think. But, and this is the important point, nature thinks very much faster than we do. When you watch my eyes blink, the moment seems almost to have no duration. But while my eyes went down and up, molecules in my eyes vibrated 10 billion times. For each molecular vibration, electrons in the atoms orbited 1 million times. For each electron orbit, the protons in the nuclei orbited another 1 million times. And for each proton orbit, the quarks within the protons orbited another 1 million times. The range of timescales is absolutely vast. To the electron in the atom, my eye blink seems like continental drift. And to the quark in that proton, the electron seems frozen in time. Nature thinks enormously fast, and those first nanoseconds in the life of the universe were like geologic eons to nature. And within those eons, enormous changes could take place slowly and deliberately. So when, in the next few lectures, we go to ever earlier times, try to think of these times not as imperceptible instants, but as geologic eons in which whole continents are built and eroded. Now, I see I have a couple of minutes left, so let me briefly review. In the next few lectures, we're going to be exploring the first second in the life of the universe. If we start with the conditions during helium synthesis, around a minute, then the known laws of physics allow us to extrapolate back in time to ever higher temperatures, reaching millions of billions of degrees in the first nanosecond. Perhaps surprisingly, we can recreate these temperatures here on Earth using particle accelerators. And over the past 50 years, we've steadily built up a working knowledge of how matter and energy behave in these early times. And it's possible to follow the properties of the expanding furnace in some detail. Now you've got the overall framework, the next lecture, we're ready to follow the changes in particle populations. And in the lecture following, we'll look at the emergence of the four forces, as well as encountering several places where we need to go beyond the standard model.